Thanks for staying with us. Today we'll present a 3D geodynamic modeling for the central western Himalaya. Our work will highlight how the arcuate shape of the Himalaya range and the along strike mechanical heterogeneity can facilitate non-plane strain and some and development of some non-cylindric structures, including a regional metamorphic complex. So in the Himalaya, the major rock units and the major shear zones is very continuous along the strike. And previous study also considers that where's my cursor? The Himalaya has a perfect arc shape. So many tectonic studies were conducted along the transections of wedge normal directions. But actually, there are many features suggest it's much more complex. There are wedge parallel strain, and the structures are non-cylindrical. There are long strike change in the tectonic settings. Here I labeled 6 representative features. The feature number 1 here is the Guru-Medata metamorphic complex. It accommodates the wedge parallel extension of in northwest-southeast direction. And because the Himalaya is sitting on the under-thrusting Indian plate, so the extension is not at a whole lithosphere scale. And actually it has a thickened footwall. That's the pink color is the footwall, and that's the high-grade metamorphic core of the Himalaya. And there was a contrasting difference in tectonic settings across its structure along the strike. To the west, you can see feature number 2 and feature number 3. There are a super-detachment basin and a dome with normal faults. This is Zada basin, this is Liu Pajil dome. They all are products of wedge parallel lengthening strain. And in the footwall of the metamorphic complex, you can see the high-grade rock. The exposure extends further to the east, and it lines up very well with this a series of domes. People usually call it the North Himalayan antiform. These domes are also composed of thickened high-grade rocks from middle-lower crustal depths. So there's a very different tectonic setting across this metamorphic complex. And on this map, you can see the feature number 4 is the embankment feature in the western Nepal. This embankment feature is along the active uplifting front, defined by a high slope zone, the red color on this map, and the concentrated seismicity and the surface geology. And that is to the south of, that's approximately here on this map, to the south of the metamorphic complex. And along the eastern limb of this embankment feature, there's a transtensional active fault system called Western Nepal fault system. So the Guru-Medata metamorphic complex, where's my cursor? Yeah, it's also like a step over between the Himalaya rear and this active transtensional fault system. So you can see all these features suggest that the Himalaya range is much more complex than a perfect arc. And all of this indicates wedge parallel strain, and the structures are non-cylindrical. So how to reconcile these features in one geological model? Here's our hypothesis, and the pictures on the right show our geodetic model design. In this model, we want to test the 2 main factors. The first one is the arcuate shape of the Himalaya. We think that because of the arcuate shape, the obliquity increased to the west. So there must be a increasing gradient in the wedge parallel strain, so that can generate the super-detachment basin and the normal fault and this metamorphic complex. And the other feature, the other factor is in western Nepal, there's a wider strongly coupled segment of the basal detachment. That's about here. So we think that feature generated the embankment feature of the active uplift front, and that also pushed the middle-lower crust thickening further to the hinterland. So that's the footwall of the metamorphic complex. So it's really 3D structure here. And the combination of these two factors, the arcuate shape and this mechanical heterogeneity, generated that western Nepal fault system along the eastern limb of this embankment feature. In the model design, I have two panels. The left panel shows the boundary conditions, and that is the basal surface of the model. The right panel shows the mechanical properties of the model. That's the upper surface of the model. And two cross sections are along the eastern side of the model. And in the model, we don't simulate the building up process of the topography, so we use a predefined free surface. So which means all the material flow through the surface get eroded immediately. In the model, we let the material flow from the southern side. This side is open, and we let the other three sides closed. And at the bottom of the model, at the rear of the origin, we open a small window to let the mantle lithosphere get subducted by flowing out from the system at the same rate as they flow in from the southern boundary. So basically, only the crustal material can get involved into the deformation in the wedge. And this window follows the arc shape of the origin, and the convergence obliquity increased westwards from the 0 degree to about 22 degree. And on this plan view, the different color represent the different mechanical properties. We only have one viscous layer that's here. There's a weakened middle row crust beneath the thickened Tibetan plateau, and all other parts are frictional materials. The strength of the material was defined by the internal angle of the internal angle of friction. So the friction efficient equals tangent of the frictional angle. And the white parts are strong Indian and Tibetan crust. And for the origin part, we divide that into three important parts. That's a rear shear zone, a wedge, and a basal detachment. So in the testing models, we only change the properties of these three parts to see how they can affect the deformation distribution within the wedge. Because we also want to simulate the effects of strong detachment in one sector, so we further subdivide the basal shear zone into three segments along the strike. And the sector 2 is generally stronger than the identical sectors 1 and sector 3. We use the modern software DORA. So this software can calculate the velocity of the material and the strain rate distribution. So from which we can interpret the tectonic setting at different parts. This table shows how we change the mechanical property of the three parts for three sets of test models. But I don't have time to present all of this. I will only show you the model 15, which is slightly modified from the test models. And all the numbers, all the parameters are annotated here. And the modification is that for the basal detachment, we applied a long strike varied strain softening process. This graph shows how it works. For the both strong and weak sectors, we let the friction angle decrease linearly as the strain accumulates. But for the strong sector here in this sector, the softening is way slower than the weak sector. So that's different from test model in which I directly defined the two different numbers for each sectors. So now I'm going to use a couple of videos to show you the modern result. In this video shows the y direction velocity. Y direction is the west direction to the west. So you will see how the deformation evolves as the strain softening process develops. And in all my videos and the results pictures, the black arrows represent the instant velocity field. So you can stare at one like here, one arrow to see how it changed the direction as at that point get involved into the deformation. So now I'm going to play the video, and you can compare that with the conceptual model. So you can see as the material gets involved into deformation in the western sector, it gets a component of westward direction velocity, and there's a westward increasing gradient in this in the y direction velocity, and at the same time, because of the along strike heterogeneity in the battle shear zone develops, we got an embankment feature here, and also along the eastern limb we have high y direction velocity that correspond to the translational setting there, correspond to the western dipole fault system. And this westward gradient is missing in this sector 3, which corresponds to the central Himalaya of low or no obliquity in convergence. So now in this video, I'm going to show you the z direction velocity, which is the vertical direction. So you can consider that as a thickening. Again, you can see as the mechanical heterogeneity develops in the battle shear zone, we get this embankment feature in the evolving uplifting front. But there's always a high velocity zone to the north of this embankment that corresponds to the footwall of metamorphic complex. So I'm going to use two snapshots to summarize the result. The two snapshots are about 10 million year and 18 million year in the modeling time. I also put the numbers of features in the corresponding locations for comparison. So there are 3 panels at each time. The left panel is the strain rate map. The middle panel is the y direction velocity or westward direction velocity of the material. And the right panel shows the vertical velocity. Again, in the western sector, because of westward increasing obliquity, we have gradient in the y direction velocity, so that indicates wedge parallel extension. So that's where we find the Zada basin and a dome with normal force. That's the wedge parallel extensional feature. And you can see feature 4 is this embankment. It develops as the along strike heterogeneity in the battle shear zone develops, and it's evolving with the active uplift front. Also, along the eastern limb, this part that corresponds to western dipole fault system, that combination effect of the Arcuate shape and this along strike heterogeneity. And this model also predicts that this translational evolves with the active uplift front. So that will also predict that the segments of this structure system, the northern segments should be older than the southern ones and can accommodate more motion. So that's basically consistent with our preliminary field mapping in this area. And the feature 6 is here in the sector 3. That corresponds to the northern Himalayan anticline. Because there's not as much wedge parallel lengthening strain in that sector because obliquity is so low. So the earlier thickening there in the hinterland can be preserved. So in conclusion, our model suggests that oblique convergence along the Arcuate wedge and along strike mechanical heterogeneity in the base of the wedge can generate complex non-cylindric strain. And the distribution of the deformation in the wedge is very sensitive to the mechanical property of the basal shear zone. And our model can produce an evolving strain field that can explain the formation of several first-order regional features in the central western Himalaya, including a regional metamorphic complex and many structures around it. Thanks for your attention. And this work is not published yet, but the general idea was described in the other 2 published papers If you are interested, check them out. Thank you.